All right, so we've just finished talking about what a NMR spectrum looks like and the type of information that we can get from it. Now, before we get to it, have fun investigating these sort of spectrums, we do have to talk about something important. And this is going to help us figure out how many signals we would expect to see from a compound. And the problem is that every hydrogen may not generate its own signal. There may be some redundancies, and that is due to chemical equivalence. And so that's the next topic. So chemical equivalence has to do with the fact that sometimes hydrogens, and this is specific for proton NMR, but it also can be relevant in carbon NMR. But right now we're just talking about proton NMR, which is with hydrogens. And that is that some hydrogens can be considered equivalent to each other. And that is that you have two hydrogens, or maybe even more, 3, 4, 5 hydrogens, that are chemically equivalent, so they only generate one signal. Let's take a look at an example of how this sort of comes about. So let's just first consider this molecule right here. And notice it is just propane. This molecule is propane, and there's hydrogens all over this molecule, but I've just indicated two hydrogens here in the central carbon. And let's say I ask the question, what is the relationship between these protons? That's the key question. And to find out the relationship between those two protons, we have to do something called the substitution test. And the substitution test is extremely easy. All you need to do is redraw the compound, and one of the hydrogens in the first compound, replace it with a D. And the D is just a deuterium, but really it's just something unique, something different. So you can just say D stands for different, okay? D is chosen because it's not commonly found in compounds normally, so it's just something different, okay? Then redraw the compound and replace the other hydrogen with the D. And now what you want to do is find out what is the relationship between these two new compounds that you've drawn. And we'll do lots of examples like this, but what would be the relationship between these two compounds? There's only three options. Either they're the same compound. In that case, the relationship between the protons is said to be homotopic. Or they're enantiomers. If the two compounds you've drawn are enantiomers, the relationship between the protons is said to be enantiotopic. And if the compounds are said to be diastereomers, they are diastereotopic hydrogens. So in this case, they are homotopic, and we can see that why. How many stereocenters are in this compound? 0, right? There's no stereocenter in this compound. We've got two methyl groups that are identical, and so this isn't a stereocenter. So when we flip the wedge and the dash, it doesn't actually change the stereochemistry because there is no stereochemistry. It's not a chiral molecule, so it's the same compound. In fact, you can just see if you take this compound and flip it over 180 degrees, you would get this compound. And if you can just interconvert two compounds by flipping them, they are the same thing. So this is homotopic. And so the relationship between these two hydrogens is said to be homotopic. And we found that out using the substitution test. By the way, if you have protons that are homotopic or enantiotopic, they are chemically equivalent for NMR, and so those protons will only generate one signal in the proton NMR. Diastereotopic protons, however, are chemically different, so we'll talk about that. Let's do another example here. Let's consider these two hydrogens on this alkene. Let's do the substitution test to figure out the relationship. Remember, in order to do these types of problems, I have to indicate two hydrogens. Okay, so we'll redraw the compound twice. First, we'll replace the top hydrogen. We'll replace the top hydrogen with a D, and then we'll replace the bottom hydrogen with a D. And then what's the relationship between these two compounds? Well, these are diastereomers. Remember that diastereomers don't have to be necessarily chiral compounds. In this case, alkenes can be diastereomers. That was one of our early definitions of stereoisomer, was these alkenes being E or Z. So remember that E alkenes and Z alkenes are diastereomers of each other. And so these are going to be diastereotopic hydrogens in the original compound, which means that these two hydrogens will each give a unique signal in the HNMR. Let's do another example. Okay, let's consider these two hydrogens on this alcohol. We'll do the substitution test. We'll replace one of the hydrogens with a D, and then we'll replace the other hydrogen with a D. So when we replace the left hydrogen, we get the first compound. And if we replace the right hydrogen, we get the next compound. What's the relationship between these two compounds? These are enantiomers, okay, because we do have a stereocenter now. Because we have 4 unique attachments, we have one stereocenter, and the one stereocenter is switching The wedges and the dashes flip. So these are enantiomers. So these two hydrogens in ethanol are enantiotopic. I have another example here. It's another alkene. I've indicated these two hydrogens. Let's do the substitution test. Replace one of them with a D, then replace the other one with a D. What's the relationship between these two compounds? They're diastereomers, so those two hydrogens are diastereotopic. Awesome. Okay, let's take a look at some more examples. And there's some problems on your NMR problem set where you're going to have to decide the relationship between the indicated protons. All right, let's take a look at the next page here. Now, I want to mention before we do a deep dive into some examples, there are two distinct scenarios for this chemical equivalence test. Either the hydrogens are on the same carbon, or the hydrogens are on different carbons. And of course, I indicate the hydrogens. Okay, so let's take a look at a scenario one. Scenario one, let's say I ask you to find the relationship between these two hydrogens on this molecule here. In scenario one, when the hydrogens are on the same carbon, you just do the substitution test and compare directly, okay? So let's take a look. We'll replace one of the hydrogens with a D, then we'll replace the other hydrogen with a D. Now pause the video really quickly, if you like, and try and figure out what's the relationship between these two compounds. Are they the same compound? Are they enantiomers, or are they diastereomers? Okay, I gave you a chance to pause, so now I'm going to tell you the answer. Is this a stereocenter? Does it have 4 unique attachments? Yes, it does. It has a carbon here, that's unique. It has a carbon down here, that is unique because it's farther away from the chlorine. We have a hydrogen and a deuterium. So we have 4 unique attachments. And so we have one stereocenter, and it changed. It flipped from wedge to dash. So what that means is that we had one stereocenter. How many changed? One of them changed. So all of the stereocenters changed. So enantiotopic. Easy, right? As long as you can tell the difference between enantiomers, diastereomers, and the same compound, then these sort of problems are really easy. Okay, let's take a look at the next one here. Scenario 2. In this case, I'm asking you to compare hydrogens on different carbons. In this case, don't compare directly. I suggest you flip, then compare. Let me show you what I mean by that. So let's say I asked you to compare the two hydrogens in the cyclohexane. Well, it's a little difficult to compare them in the chair, so let's redraw it as the flat form. And I'll go ahead and replace one of the hydrogens with a D. And then I'll redraw the molecule and replace the other hydrogen with a D. So I hope you're okay with me converting the chair into the flat form and then drawing the two compounds that are part of the substitution test, replacing one of the hydrogens with a D and vice versa. Okay, now comparing these two compounds can be a little bit tricky. So what I suggest you do is flip the second compound you draw to try and line the hydrogen over the hydrogen and the D over the D. So can you imagine taking this compound and flipping it 180 degrees? The hydrogen will flip over to where the D is, and the D will flip over to where the hydrogen is. And in the meantime, the wedges and dashes will also flip because, imagine the hydrogen's facing backward right now. If you do a 180 degree flip, look, now it's facing forward. So that means that after we do the flip, we'll get this compound here, and then now compare these two compounds. Are they the same compound? Are they enantiomers, or are they diastereomers? Well, we have how many stereocenters? Well, we really don't have any stereocenters in this compound, right? Because, for example, this doesn't have 4 unique attachments. The carbons on the left and the right are the same. But you can clearly see, just looking at these two compounds, they're identical, right? It's the same compound written twice, so that would be homotopic. Okay, so that's what I mean by scenario 2, where the hydrogens are on different carbons. We flip and then we compare. All right, so why don't we now look at some examples and do it a little bit more slowly and just do more problems like this, okay? Let me just pull up some problems right now. Oh, I already have them written in your notes here. Okay, so let's try this first one here. The first one, the two hydrogens are on different carbons, so we are going to have to do the flip and then compare trick. So I'll start out by redrawing the compound. Okay, and I would like you to draw along with me. And so now what we're going to do is we're going to replace one of the hydrogens with a D. So I'll just go ahead and replace the left one with a D and leave the right hydrogen the same. And then I'm going to draw the compound again. This time I'm going to flip the other H to a D and leave the left hydrogen the same. All right, now, what's the relationship between these two compounds? Well, like I said, I recommend, if this is scenario 2, the two hydrogens are on different carbons. It would be a good idea to flip and then compare. So let's do a little flipperoo here. And I'm just going to sort of pick up this molecule by the OMe group and twirl it. So it's going to kind of look like, if I draw a little 3D version of it twirling, might look something like this. Can you kind of see it's like spinning along this axis here? And when we do that, the D is going to go over onto the left side. And the H is going to go over onto the right. Okay, now we compare these two options. What's their relationship? They're the exact same compound. So that means the two hydrogens that we initially identified were homotopic. I found out that a lot of times they leave this out of the 211 curriculum because it's too difficult for students. Or I think you guys will find this just fine. It's not too difficult. Let's do another example down here. Let's do our substitution test on this compound down here. Okay, so we'll just redraw the compound. And I'll replace one of the hydrogens with a D. And I'll leave the other one an H. And then I'll redraw the compound again. I'll put the D on the wedge this time. The D on the dash, and the hydrogen will be on the wedge. Okay, what's the relationship between these two compounds? Well, how many stereocenters do we have? We've got one stereocenter here. Did it change? Yes, it did. So we've got one stereocenter and one stereocenter changed, so that means it's enantiotopic. When all the stereocenters change, you've got enantiomers. Let's do another example here. We'll go ahead and replace one of the hydrogens with a deuterium. Okay, put the deuterium on the top, on the dash, and I'll keep the bottom one an H for now. Redraw the molecule again. It's kind of annoying to have to redraw the molecule, I know, but this is the best way to tell homotopic, enantiotopic, diastereotopic. Okay, this time I'll replace the bottom one with the D and leave the top one the same. Okay, what's the relationship between these two compounds? Well, how many stereocenters do we have? We have a stereocenter here, and we have a stereocenter here. So we have two stereocenters. And how many changed between our two structures? Just this stereocenter. Only this stereocenter changed. This stereocenter stayed the same. So what do we say when some but not all the stereocenters changed? Those are diastereomers. So those two hydrogens were diastereotopic. Are these free points or what on an exam? So easy, and you end up getting a lot of points for these too as well. You also have a lot of points that you can lose, so make sure you understand this and don't get these wrong. I do put these on exams, even though this is technically part of the lab component of the class. They do show up on exams from time to time. Okay, let's do another one down here. Again, we've got a scenario 1 in that the two hydrogens are on the same carbon, so I'll replace one of the hydrogens with a D. This time I'll do the dash one first, why not? And then I'll redraw the molecule once more, replacing the other with the D. Okay, what's the relationship between these two compounds? They're enantiomers. We've got one stereocenter here, and it changed, so we have enantiomers. So this is enantiotopic. Let's do a couple more. Just two more. Okay, we have another scenario 1. The two hydrogens are on the same carbon, so I'll just redraw it. And H here. and a D here. Keep the wedge and the dash in the same positions, but I'm just going to replace the D and the H. What's the relationship between these two compounds? Well, we don't have any stereocenters, right? Be careful. This is not a stereocenter because we have ethyl groups to the left and right. So we have 0 stereocenters, so none of them are changing. So this is homotopic. Right? You could just interconvert these two compounds. If you just took this compound and flipped it 180 degrees, it would line up perfectly with this compound. So in other words, it is superimposable with its mirror image, so it's not an enantiomer. These are homotopic, same compound. All right, last one here. We have a chair. So whenever you get a chair, just turn it into the flat form. Okay, and we have a hydrogen that's going up as a wedge. I'll leave that as an H. And then we also have a hydrogen going down 2 away as a dash. I'll replace that one with the D. And then I'll redraw the molecule. This time I'll replace the top one with the D and leave the bottom one as the H. I'm supposed to put that in red. You don't have to color code or anything. I'm just doing it to help you see. Okay, what's the relationship between these two compounds? Remember, don't compare until you flip. So let's go ahead and flip this compound around this axis here to put the H where the D is. And if I do that, the H, which is going to be a dash, is going to become a wedge. And the D, which was a dash, is going to flip down and become a dash. It was a wedge, now it's a dash. Okay, what's the relationship between these two compounds? They're the same damn thing, so this is going to be homotopic. All right, now that we know that, now we can answer a harder question, which is if I give you a molecule, how many signals will it produce? Let's take a look at that. So homotopic and enantiotopic protons are what we call chemically equivalent. And that means they only produce one signal in NMR. Versus diastereotopic protons, they produce different signals. So let's do an example of a really hard problem here, which asks the question, how many proton NMR signals would be expected of this compound here? Okay, the first thing we need to do is draw in all the hydrogens. So let's do that. You can never have more signals than you have hydrogens, but you can have fewer. So we need to draw in all the implicit hydrogens. So let's go ahead and do that. Okay, and I'll draw them in blue. So we have an H here, an H here, and we have an H here. All right. So now let's figure out how many signals we're going to have. We can have as many as 3 signals because we have 3 hydrogens, but we can have as few as 1 signal if all the hydrogens are chemically equivalent. Okay, so one thing's for sure, this hydrogen is unique. It's on its own, it's in its own unique chemical environment. There's no hydrogen like it. It's connected to the double bond, it's in a unique chemical environment. So I'm going to go ahead and label that HA. Now the question is, these two hydrogens. Are these two hydrogens the same, chemically equivalent, or are they different? Are they diastereotopic? So let's answer that question by doing the substitution test. I'm just going to do a quick substitution test here. I got D in my H versus H in my D. Okay, what's the relationship between these two compounds? they're enantiomers, right? We have one stereocenter here, and it's flipping. So that means that these two hydrogens are enantiotopic, which means that they are chemically equivalent, because homotopic and enantiotopic protons are chemically equivalent. So that means this will just be HB, and this will also be HB. So there's only two different types of protons in this compound. So that means the compound will produce two signals. So that's your answer, two signals. All right, let's take a look at a trickier one. Let's take a look at a trickier one. I see I've used up too much space, so I'm just gonna move it all up a little bit. Oh no, that's okay. I'll just start a new page. It's fine. We'll just start a new page. We won't crunch it all in here. Okay, let's do another one here. Let's try this compound here. Okay, that's good. Okay, let's do this compound here and figure out how many signals this compound is going to produce on the proton NMR. So first things first, we need to draw in all our hydrogens. So I'll go ahead and do that. I'm going to zoom in here. All right, now on this carbon here, we have 3 hydrogens, so I'll draw those in. Okay. We have a hydrogen not shown, but it's dashed right here. We have this hydrogen on the OH group. I'll highlight that in blue. Don't forget the OH is still a hydrogen there. Okay. We have a hydrogen down here. And we have hydrogens over here. Okay, so we have a total of 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, which means we can have a maximum of 8 signals. But it turns out we're going to have fewer than that. Okay, let's start by identifying obviously unique hydrogens. Hydrogens that are clearly in unique chemical environments. So this hydrogen is clearly unique. It's the alcohol hydrogen. This hydrogen is clearly unique. It's just kind of on its own, sandwiched in its own little world there. This hydrogen is clearly unique. It's kind of sandwiched in its own world. But we do have an issue with these 3 hydrogens and these 2 hydrogens. Are they grouped together? Well, it turns out that methyl group hydrogens are always homotopic because they always are never part of a stereocenter, because there's always 2 additional hydrogens on there, even if you do the substitution test. So save yourself the time. Methyl groups are always homotopic within themselves. So if you see a methyl group, just assign them all 1 letter. In this case, they'll all be assigned D. Methyl groups are always homotopic. So I'll just even write that out here. Methyl protons are always, no exceptions, homotopic with each other. Okay, now that just leaves these 2 hydrogens over here. What is their relationship? Well, I can tell you, here's a little quick shortcut. These hydrogens are diastereotopic, and I can tell that without even doing the substitution test. You want to know how I can tell? Take a look. One of these hydrogens is closer to this wedged OH group. Can you see that? Because they're both wedged. That means that they're going to be in a different chemical environment from each other. This hydrogen is further from the wedged OH. Whenever you have that situation where you have another stereocenter somewhere else in the molecule, it makes all of these CH2 hydrogens diastereotopic because one hydrogen is always closer to that other stereocenter than the other. So without even doing the without even doing the substitution test, I can tell that this is going to be different than this hydrogen here. Right? And again, the reason is that this hydrogen is wedged just like the alcohol. So it's in a different chemical environment than this hydrogen, which is dashed, unlike the alcohol. So that's diastereotopic protons. Okay, so how many signals did we generate? Let's count the letters. 1, 2, 3, 4, 5, 6. 6 signals. Awesome. All right, let's do some more examples here. Let's do 3 more examples of this, and then we'll be done with this part of the lesson. Okay, the next example is how about this guy right here? Let's start by drawing in all the hydrogens. Okay, we've got 2 methyl groups on either side, but they're different methyl groups, but they're homotopic within their own little groups. So what that means is that these are all going to be HAs over here, and these are all going to be HBs over here. Okay, now what about these 2 hydrogens right here? What's their relationship? They're going to be enantiotopic. How do I know they're not diastereotopic? Well, if they were diastereotopic, they would be different in different chemical environments. But I don't see any other chiral centers in the molecule, which means that this hydrogen, for example, is not going to be any closer to anything than this hydrogen. But let's still do the substitution test just to be sure. So I'll replace one of the hydrogens with a D, and then I'll redraw the molecule and replace the other hydrogen with a D. This is just to be safe. And now what's the relationship between these 2 compounds? They're enantiomers. We've got one stereocenter and it's flipping, so they're enantiotopic, which means these 2 hydrogens are chemically equivalent. Remember, enantiotopic protons are chemically equivalent, so this is going to be C and C. And I'll just put a note here that these guys are enantiotopic. Okay, so that's going to mean this compound is going to give 3 signals, A, B, C. All right, let's take a look at another compound here. Oh yeah, this is a good one. Okay, let's draw in all the hydrogens. Okay. Now, because of symmetry, the methyl groups on the left and right are equivalent with each other. It's a completely symmetric molecule, so we need to build from the outside in. And so we can see that, of course, within themselves, the methyl groups are going to be the same. But because the molecule is totally symmetric on the left and the right, the chemical environment is no different on the left side of the molecule than it is on the right side. So these are all A's as well. All right. Next up, we've got some enantiotopic protons here and here, just like before, just like in this example here. But because of symmetry, they're all equivalent with each other too. So those are all going to be HBs. And then finally, these 2 hydrogens in the middle, they're also actually, these are homotopic because there's symmetry on the left and right here. So there would be no stereocenter if you did the substitution test on these 2 central hydrogens. Those are going to be C and C. So this compound is going to give 3 signals. All right, let's do one more just for fun. How about this compound here? Okay, let's draw in all the hydrogens. Okay, we've got our 3 hydrogens up here. Okay. Obviously, those are going to be unique. These 2 hydrogens are homotopic with each other. As we build outward here, they're the same by symmetry in the exact same chemical environment. Those 2 hydrogens are the same, and then this hydrogen down here is unique. So this is going to give us 4 signals. All right. So that's pretty good stopping place for us now. You can go ahead and now you can start the NMR practice problems. There's going to be some practice problems where you're going to have to determine homotopic and antitopic and diastereotopic for a little bit of practice with that. And then also I'll give you some compounds and you'll have to tell me how many signals you expect them to produce in the proton NMR, and you'll have to do the analysis that we're doing here. Great practice. Check it out. And then when you're done with that, check back in for the third and final part of NMR spectroscopy for this week.